10C, we're going to look at correlation, causation, and then prediction intervals. So, some definitions. Correlation is when there is a relationship or association between two variables. So anytime we look at a scatter plot and it has a shape, a linear shape, a nonlinear shape, doesn't matter. As long as there is some association there, we can say there's correlation. All right, but causation is when we can say one variable is the direct cause of change in the other. All right, so the height of a toy tower increases as we use more Lego bricks to build it. All right, if you increase your time training, then the amount of time it will take for you to run a mile will decrease. All right, these are what we call causal. That's that word right there, causal, not casual. All right, causal relationships. Okay, if I spend more time training, that will cause my mile time to go down. All right, but something very, very important that if you learn nothing else in this class, make sure you learn this. Correlation does not equal causation. Just because there is a relationship between two variables does not mean that one of them is causing the other to change. Okay, so let's look at some examples. All right, here we have in red the per capita cheese consumption, and in black the number of people who died by becoming tangled in their bed sheets. If you look at those two lines, they match each other pretty closely. Okay, but I don't think anyone could argue that eating more cheese causes people to die by being tangled in their bed sheets, or vice versa. All right, having people die by becoming tangled in their bed sheets does not cause people to eat more cheese. Okay, so this is a correlation, but there is no causation. Okay, here's my favorite example. The U.S. unemployment rate from 2013 to 2018. And in 2013, Britney Spears released a song called Work Blank. I'll let you go look that up and figure out what word is supposed to go there. And as soon as she did that, the unemployment rate took a steady decline. So Britney Spears told people to get to work, and they did, right? I mean, clearly we're joking here, okay? But another example of correlation does not equal causation, all right? Britney Spears' song did not cause more people to be able to get jobs. Okay. Now, sometimes correlation can be completely random, which is the last two examples that I told you. They're just silly and randomly correlated. Other times, there's what we call a confounding or lurking variable. All right, meaning there's something not included in our study that could change both of our variables that we're looking at. So here's an example. There was a study that found people who exercise more contracted skin cancer at a higher rate. All right, but it's difficult to say that exercising causes an increased risk for skin cancer. So they did some more study. Okay, and they discovered that people who live in warm climates exercise more than people who live in cold climates. Well, that makes sense. All right, it would also make sense that if you live in a warm climate, you are at increased risk for skin cancer. Okay, so it was actually the warm climate that's the confounding variable. It was causing the amount of people that exercise to go up, and it was also causing the amount of people with skin cancer to increase. Okay, so that's an example of a confounding or lurking variable. Okay, we are going to calculate what is called a prediction interval. Okay, so we have done, we've looked at scatter plots, and let's say my scatter plot looks like this, and then I draw a line of best fit through there, and then we've used that line of best fit to make predictions, saying if X is here, then what will Y be? All right. Remember, this line is not exact. It doesn't go through every single dot in our scatter plot. It's just sort of an average. So what we So what we can create is sort of an interval. Like it's not, I know it's not going to be probably exactly this, but maybe it's a little higher, maybe it's a little lower. So if X is whatever this is, 17, then Y is going to be somewhere between these two numbers, okay? And so it's very similar to a confidence interval. We have a percentage. So if we make a 95% prediction interval, then we are 95% sure that our true value is somewhere in that range. Normally we do this with statistical software, but because we don't do that for this class, we're going to use an Excel spreadsheet. It's called the Prediction Interval Calculator, and it's in Canvas for you to download and use to do these problems. Okay, so here's our steps, and I'm going to pull up that Excel sheet. And so when you're using this, it's very important that you only type in the correct spaces and don't delete other things, because it will mess up the formulas that are being used to calculate these numbers. Okay, so you're going to put in X and Y values, and then you're going to type something in these four yellow boxes: slope, y-intercept, t sub c, and then the X value that we are using. All right, so let's do an example. The table shows the amount of crude oil produced in the US and the amounts of crude oil imported by the US. And then they gave us the equation of the regression line, or line of best fit. And then here's the table. We're going to construct a 95% confidence interval for the amount of crude oil imported when the amount produced, and amount produced is X, is 5,500. So I know that if I plug 5,500 in for X in this equation, that number is not exact. So I want to know what's a 95% interval for what I think that number could be. Okay, so first thing we're going to do is we're going to go in this Excel sheet, and we're going to type these numbers into the X values and Y values. So you guys go ahead, pause here, and do that now. So all I did was type in those numbers from the table, and then anything extra I can delete. So this is the one thing you can delete. So I can go in there and I'm just going to press the delete key, all right, and erase those things. Okay, then we need the information from the line of best fit. So from my problem, the slope was negative 2.735. So I'm going to put that in here. So negative 2.735. And then the y-intercept was 27,657.823. So 27657.823. Okay, you can see these numbers are changing, but they're not good until we're done entering all our information. All right, T sub C, that is the value from the T table. Remember using that a couple units ago. So I'm going to pull that T table up. You guys can grab that from Canvas. All right, so if you remember this thing, it has degrees of freedom on the left, confidence level on the top. For prediction intervals, the degrees of freedom are n minus 2. So if I go back to my problem, I have 1, 2, 3, 4, 5, 6, 7. I have 7 data points. All right, so 7 minus 2 would be 5. So I have 5 degrees of freedom and a 95% confidence level. My T value is going to be 2.571. So underneath this in the T value, I'm going to put 2.571. And then the last thing that I need is the X value. So they asked me to make a prediction when X is 5,500. Okay, so in that X value, I'm going to type 5,500. Okay, and so here is my interval. All right, my interval goes from 11,783.05 to 13,447.60. All right, and just like we did with confidence intervals, we can write those in parentheses. All right, so my 95% prediction interval when the amount of oil produced is 5,500 is 11,783 to 13,447. Okay, and so what that means is we have a sentence that we could fill in. So that means that I am 95% confident that when my explanatory value, which is my X values, so when the oil produced, okay, so when oil produced is 5,500, that's the one we made a prediction for. All right, the oil imported, that was my response variable, will be between, and then my two numbers were 11,783 and 13,447. Okay, and so this is just like we did with our conclusions for hypothesis testing. This is a sentence that you can use every time to interpret and fill it in.